So my presentation just tries to put everything together with one analysis to look at traffic-related air pollution and pregnancy loss. This is a work that we've been doing for 2.5 years now with Mark, Rana, and Ander. Traffic is a particularly toxic source of air pollution for not just reproductive outcomes, but for many, many outcomes. But specifically for pregnancy outcomes has been very consistently linked to preterm birth, birth weight, small for gestational age, preeclampsia, stillbirth, potentially even many more other outcomes. The relationship with miscarriage, though, is harder to establish. As Mark said, there are only very few studies looking at this with limitations. Miscarriage is the most common pregnancy complication, almost 20%, some estimates say higher, of all clinically recognized pregnancies will end in pregnancy loss. But current analytic approaches to study these miscarriages or losses require, for the most part, that they are identified in the medical system, which is a problem when even occasionally the mother might not even know she's pregnant. And incomplete identification of these losses prohibits comprehensive investigation of the risk factors for pregnancy loss and could even induce bias in the estimated effect, both for pregnancy loss, but as Jan and Ranan said, also in other outcomes later in life. Very, very few studies have looked at the air pollution pregnancy loss association, and all of them have important limitations, the major one being that the losses needed to be identified through the medical system. Many out of the very few, but some have used inappropriate statistical methods, mainly just reporting correlations instead of actual adjusted analysis. There is the potential of following women from before they become pregnant to when they are pregnant and getting biosamples of them to exactly identify when a pregnancy loss might occur. But these studies tend to be of very small sample sizes, and this, you can imagine, is a very highly selective population that agrees to do that. And none of the existing studies has looked at critical windows of exposure that air pollution can impact pregnancy loss. To date, to our knowledge, no study has comprehensively, so avoiding or overcoming these limitations, investigated this association. So this is the gap that we are trying to address. Mark showed you this. This is a very brief overview of the study design. In the top panel, these are the live births as they occur. In the middle panel, we've subtracted the gestational ages from these live births to construct these weeks, conception weeks now, that are aggregated numbers of live birth identified conceptions in a week. And then we follow these through gestational age for the next 40 weeks. In the third panel here, the exposure of interest was NO2. So again, our outcome is this live birth identified conceptions, or LBIC. We used information on two very independent locations just because this was so new. So we wanted to make sure that what we see is reproducible. So we used information from Boston between 2000 and 2003 using live births that occurred at one hospital that's near downtown Boston. We extracted the date of birth, the maternal residence zip code, and gestational ages from the birth certificates. We used information on women who lived within 60 kilometers of the hospital, and to reduce potential exposure measurement error, also women who lived within 20 kilometers of the hospital. And then separately, we used information from Tel Aviv district in Israel for a shorter time between 2010 and 2013, because that's when data were available. We used all live births of women with a home address in Tel Aviv district, and we used the date of birth and gestational age to, again, construct these live birth identified conception weeks. For our exposure data, we used NO2 as a traffic emissions tracer in both locations, but the exposure assessment in the two locations was done completely differently. In Boston, we used information from 5 state urban monitors. We downloaded the data from EPA's air quality system database, and these are hourly data. We created citywide average weekly exposures. And then we also downloaded temperature data from the airport. In Tel Aviv district, we were able and used well-validated spatiotemporal prediction model with a very high spatial resolution to get the district-wide weekly exposures. Again, this model provides hourly data that we then aggregated into weekly exposures, and temperature was available from the Israeli Met Service. Come on, there. So for health models, we run a time series with distributed lags to assess whether week-to-week variability in our exposures, nitrogen dioxide, was associated with week-to-week changes in these LBICs, live birth identified conceptions. We used the Poisson model with quasi-likelihood to account for overdispersion, and the DLM what we used to identify critical windows of exposure. Now, as Mark mentioned, this is a forward DLM, not the backward DLM that we are usually used to. And for confounding, this is now a time series setting. Our outcome is, the unit of observation is week, and our outcome is births per live birth identified conceptions per week. So individual level confounders cannot confound our relationship, this association. So the things that could confound this association are long-term and seasonal trends, for which we adjusted non-linearly, and also potentially temperature. There is some evidence on temperature impacting, we know it's very associated with air pollution, but also there's some evidence that it impacts pregnancy loss as well, and we use distributed lags for temperature as well, and also indicators for holidays. And as you see, the degrees of freedoms are different for each location because we specifically identified the best fitting models separately, independently in each location to make sure we have adjusted appropriately for confounding in both locations. These are just some descriptive statistics in Boston and Tel Aviv. You see the time series is much longer in Boston. The number of live birth identified the average number of LBICs per week is smaller in Boston. We have around 90. That's because in Boston we only have information from one hospital, whereas in Tel Aviv district we have everybody in Tel Aviv district, which is almost 500 live birth identified conceptions per week. The NO2 levels were slightly higher and slightly less variable in Boston, and temperature was much lower in Boston, as expected. So these are our results. On the y-axis are the rate ratio per 10 ppbs increase in NO2, and I'll just say we also assessed for non-linearities, and we didn't detect any. And on the x-axis are the gestational weeks, so the conceptions are assumed to be at 0, right? And what in the dark, the black line with a striped band, these are the results for Boston, and the dashed line with a gray solid bands, these are the results for Tel Aviv. And what you can see is that these are, despite all the differences in the populations, in the locations, in meteorology, in sources of NO2 even to begin with, these are remarkably similar results, that they have a dip around 15 and 16 weeks with 0.87 rate ratio per 10 ppbs of NO2 in Boston in week 15, and 0.82 in Tel Aviv. For Boston, these results are using the 60-kilometer radius around the hospital. To reduce the exposure measurement error, when we restricted the analysis to women living in 20-kilometer radius, the results were even more similar. These are almost identical curves, right? And actually, the effect estimates now are even more similar, 82 in Tel Aviv. The Tel Aviv results are exactly the same as before in the previous slide, compared to 84. Do we believe these results? Is there a biological plausibility for this specific window between 10 and 20 weeks, right? So maternal arterial blood flow to the placenta is not fully established until the 12th approximately gestational week, when the first trimester uterine oxygen gradient exerts a regulatory effect on the placenta, protecting the developing embryo against oxidative stress. But after this period, there is an oxidative stress burst. And the weeks 10 to 14 are a transitional period during which there's a gradual rise in the partial pressure of oxygen in the placenta that only stabilizes after week 16. And during this transitional period, the fetus may be especially vulnerable to increases in the maternal oxidative stress. And guess what air pollution does when people breathe it? It really increases oxidative stress. That's one of the major pathways of pathogenesis of air pollution. So even the critical windows that we observed may have some biological sense. So in conclusion, we use this novel study design that Mark explained in detail to comprehensively assess the relationship between traffic-related air pollution and pregnancy loss, avoiding having to rely on medically identified events. We use data only on live births. This is a very strong design where you don't actually need a lot of information on even the women or individual level factors. We did not believe the results. That's why we really wanted to have 2 locations. These are remarkably similar results that only make us more confident in what we see. We have found the strongest effect estimates for gestational weeks between 10 and 20. As Mark said, this doesn't mean that this is when the loss actually occurred. We have no idea. We do not observe the losses. But this indicates that something started happening during this period that could have resulted at a pregnancy loss, either then or later in pregnancy. So in conclusion, we found significantly harmful effect of traffic-related air pollution late in the first trimester, I should say, and early in the second trimester of pregnancy. And to link back to Rhiannon's talk, this is exactly the exact same period that they observed the protective effect of NO2 on autism in Israel. So this was work that it wasn't just the 4 of us. We needed people to help us with exposure assessment and data and understanding what we saw. So I would like to acknowledge everybody here and also our funding. Thank you very much.